opportunity to present this work here, and also for fine-tuning the weather. It definitely has been more productive for me than what it would be, so thank you. So this work done in collaboration with Rodrigo Veiga, EPFL and USP, Ludwig Stefan, Lenka, and Florent, so you know. So before I start, just a disclaimer. So this is not a talk exactly about spin glasses, but you know, about machine learning. And machine learning, there are many people coming from different communities that see the problem in different ways. And for me, coming from statistical physics, the way I see the problem is a spin glass. So this is a talk more in the direction of what Lenka and Emmanuel presented. We're going to use tools from spin glass theory to try to understand our problem of interest, which is machine learning, in particular two-layer neural networks. So why would you want to understand that? Well, because it's a very interesting system with very interesting properties. In particular, when we're dealing with neural networks, we're dealing with non-convex problems. And in a non-convex problem, algorithms matter, as we have learned in these past days. Different algorithms, different procedures to try to find the ground state is going to reach different minima that might be local or global. And that's why the tools from statistical physics and ordered systems is so useful here. And in particular, one algorithm that we're going to be interested in is SGD. So Emmanuel has introduced SGD yesterday, and SGD is actually the algorithm that is used to train deep neural networks, and it's a very non-trivial algorithm with many properties that we don't understand. So here I put one example. So SGD, when you randomly initialize, is able to find minima that is associated with good generalization. However, we know that these landscapes are full of local minima, and in particular, there are also local minima associated with bad generalization. And trying to understand why SGD goes towards this good generalizing minima when you don't force them to go to the bad ones is a big open question in machine learning, and so that's kind of a motivation for studying this algorithm. There's like no non-trivial behavior in these non-convex landscapes. It's biasing towards some properties which are good, and we don't understand why. So in this talk in particular, we're going to focus on, I would say, the simplest model which leads to a non-convex dynamics, which is a two-layer neural network, also introduced by Emmanuel yesterday. So just to set some notation, I'm going to have some inputs. I'm going to do them by X. They're going to live in RD. I'm going to have one hidden layer. This hidden layer is going to have P neurons. And then my output, for the purpose of this talk, I'm going to thinking about regression. So my output is just a scalar number. And that's how I write my output as a function of my inputs and my hidden units. So what is SGD? So SGD, our goal in machine learning would be to find good generalizing minima, as I said. So what does that mean? That means minima which, when you take a new sample, so when you take a population average over some kind of penalty, here I'm taking the square loss, I'll be taking a low number. So low population risk, low generalization error. So however, we just have samples, because we're doing supervised learning, from the distribution of the data, so we cannot actually minimize this thing directly. So what we do is that typically we do stochastic gradient descent that takes some mini batch from the data that we have received, and then estimates the gradient on this mini batch, and then takes steps in this direction. So that's just SGD. Well, there are two limits of SGD which are interesting. The first one is when the batch size is the whole size of the data set, and this limit is the gradient descent limit. And the other limit that was also quite interesting, and Emmanuel has introduced yesterday as well, is the one-pass limit. So in particular, like when the batch size is equals to 1, and in particular, you just go through your data set once. So at every step of your iteration, you're seeing a new fresh sample. And why this limit is interesting is because, well, if you do that, so if you do gradient descent, at every step you're using the same data. So you're building correlations on the estimation of your gradient. However, if you take a new fresh sample at every step, then your gradient is going to be, in the classic limit, an unbiased estimation of the population gradient. So in some sense, you are minimizing up to some noise due to the fact that you are estimating with one sample. You are minimizing the population directly, even if you don't know it. So that's might be one way of thinking of why SGD is good. So this is going to be the limit of SGD that I'm going to be studying here in this talk. So there are a few results that are well known for two-layer neural networks. In particular, when the size of the hidden layer, so when the networks are very wide, for fixed, let's think about fixed input dimension and very wide neural networks. There has been a recent line of work by May, Montanari, Shizamba, Hotskov, Van den Eyden, which more or less at the same time, that showed that actually if you write a density for the weights of the network and you track just the density, so you're modeling out the permutation symmetry of the network, you can prove that two-layer neural networks under one-pass SGD is able to reach global convergence. So actually it's able to find the global minima of the population risk. So this was a very nice result, but there is also a different line of work that is well known, especially in the statistical physics of learning literature, which is the work by David Saad and Sara Sola, which is exactly the opposite limit. So when you have fixed number of hidden units and the input dimension is very large, what they derived is some set of ODEs for the dynamics, and what can happen here instead is that here you can get trapped for very long times into saddles, and you can get trapped, for a very long time and not reach actually the global minima of the population risk. So our motivation for this work is actually to try to understand what happens between these two regimes, and in particular, since we were more familiar about this side, trying to go from this side to that side. I think going from the other side to this side is also a very interesting problem that we have been making progress recently. So if you are interested, we can discuss after. But this work, we're going to start from here and try to go there. So in particular, we're going to be studying a teacher-student setting. So we're going to be considering a data model, which we're going to call the teacher, where data, so my inputs are going to be Gaussian, and my labels are going to be generated itself by a two-layer neural network. So this is a classic setting that Lenka has introduced for us that is very, very, very practical, because we want to take averages over the data. So we need a model for the data, and that's a good model. So in particular, I'm going to be fixing the first layer weights, and my teacher is going to have k hidden units. Remember that I'm interested in studying p hidden units neural network, so I'm going to have a teacher with k and a student with p. And in particular, if p is larger than k, I should be able to learn the teacher function information theoretically. So the minimum of my population is going to be actually the teacher. So I also know what the minima is, and I can know how well I'm doing in my dynamics with respect to the best estimation. I'm also going to add some noise on the labels, just for convenience. And well, the best thing yet is like the minimum population risk actually going to be this noise, if I can recover perfectly the teacher. So that's my setting. For simplicity, I'm not training the second layer, but that's something that could be relaxed. And I'm always going to be interested in the case where the rule is realizable. So always when my student can actually learn my teacher. So what is the key idea of this line of work that started with David Saad and Sara Sola in '95? Is to realize that if you write your population risk, it's only a function of these low dimensional projections of your data in the direction of the predictor. So actually, the dynamics is high dimensional, but actually, if I'm only interested in computing the risk, I don't need to be in high dimensions. Actually, instead of taking averages over the data, if I knew the joint distribution between these pre-activations, or what we call in statistical physics local fields, then I can completely characterize this average in terms of this average of the local fields, not over the data. So the idea here, since the data is Gaussian, these local fields are going to be Gaussian, so I just need to track the two moments. And the idea is, okay, instead of tracking these high-dimensional dynamics, let's track just low-dimensional dynamics over the statistics of the local fields, or if you want, over the order parameters of the problem, if you're more inclined to physics language. So the key idea is to map one pass SGD into dynamics for the order parameters, which are the sufficient statistics for the error that we want to characterize. Okay, so now the key insight about our work is that if you do some algebra and you actually compute the self-consistent equations for the updates of these order parameters, so here we have teacher-student overlaps and student-student overlaps, there are three potentials that appear, and these potentials have different scaling with respect to the learning rate, the input dimension, and the number of hidden units. And in particular, if you look, dig deep enough into the equations, these two potentials here are the potentials that you would get if you would be doing just gradient descent on the population. So actually, these are the ones responsible for actually learning. They are going to attract you towards the good mimas. While the other one is a potential that appears due to the noise of SGD. And actually, the key idea of the work is, okay, depending on the limits we take on these factors, we are going to have different deterministic limits for the evolution of these quantities, depending on how these things scale with respect to each other. So that's our main result. We proved the theorem showing that actually you can write down deterministic ODEs for the evolution of these order parameters, and these ODEs are going to depend on how you take these quantities. And different equations for different limits on how these quantities scales with each other. And we are proving that, you know, actually the stochastic process given by the evolution of the order parameters is close enough to the solution of these ODEs. So now let's look at some results. In particular, let's consider the case where I'm scaling my number of hidden units with the dimension to a power kappa, and I'm scaling my learning rate with the input dimension with a power minus delta. And I can actually now draw how my dynamics behave as a function of delta and kappa when d goes to infinity by solving these differential equations which are low dimensional and allow me to actually draw the phenomenology for the model. So that's our phase diagram. The first thing I'd like to draw your attention to is this point. So this point is where the ODEs from sudden solo lies. That's the point delta kappa equals to 0. But there are a rich phenomenology that extends beyond this point that we were able to unveil with our theorem. So let's go in detail through them. So, okay, first let's look at this line. So this line is kappa plus delta equals to 0. And that's exactly a line that we will have the same phenomenology that Sudden Solo observed at kappa and delta equals to 0, that the dynamics, so here I'm fixing my teacher, I'm fixing my student, and I'm looking at the dynamics solving. And you can see like the dots here are actually finite size simulations, and the solid lines are the solutions of my ODE. And the behavior here is that, okay, I start learning, there is some plateau, and eventually, at order 1 times, I get stuck if I have noise in the problem. And here, what I'm plotting is not the population risk, but the population risk minus this fundamental noise. So actually, I should be able to learn and get to 0 perfectly, but what seems to be happening is that I'm getting stuck into this plateau. And this is fundamentally linked to the fact that there is this potential there that comes from the bias of the effective noise of stochastic gradient descent in this high dimensional limit that I'm taking in this regime. And this is what's getting us stuck in these plateaus in order 1 time. Instead, if we move away from this region and we get to this green region, what happens is that as I increase my system size, I'm able to get more and more towards the minimum of the population, which in this case, for this example that I'm plotting here, is 0. So perfect learning. I'm actually perfectly able to learn the teacher as I increase the system size. And actually you can do some finite size scaling to actually see that the population risk minus the fundamental noise scales to d to the minus delta. So if d is large enough, actually you're perfectly able to learn the teacher. Now there is this last region here, which is a bit less interesting. It's a region where actually this effective noise, the average of this effective noise in high dimensions, is dominating the dynamics, and I'm actually, like the teacher-student overlap is 0 for all the dynamics. I'm not able to learn anything. Still, the ODEs are well defined from the theorem. So, okay, you know, you can prove that there are some ODEs describing the evolution, but nothing is being learned. And since, okay, the finite size effects given by the theorem scales in this way, in this region, you know, I really need to go for very large D to actually see the dynamics match the simulations, but also this is an interesting region. And finally, there is also this region, which is the red region, which there are no ODs. Okay, so I see the silver is, so I'm gonna wrap up. We have these three different behaviors, like perfect learning, the plateau where the population risk plateaus at infinity, and bad learning. And what I showed you today is that we have exact and deterministic theory for one pass SGD for two-layer neural networks in this high-dimensional limit. Wide hidden layer helps achieving perfect learning, and full phase diagram describing the crossover between these different regimes. Thank you for your attention. If you have time.
Questions, like one or two questions?
Yeah. I think it was slide 9 where you showed this expectation that you can prove convergence in expectation, right?
Yeah, the theorem.
What is this infinity norm? You take the sup over T.
Yeah, it's the sup norm. But this is not very important. You can also show in L2 norm.
Okay, you have also some probability, I think?
No, we don't. But we only have expectation. But maybe if you work hard enough, you can get probability. Thanks.
I have a question myself. I mean, you have shown that the analysis of SAD and SOL corresponded just to a point. Mm-hmm. So you have basically extended the OD description to the whole region.
Yeah. Yeah, that's the key technical result. And then there is the phenomenology of these different regions, where this one is actually you are doing exactly equivalent to doing gradient descent on the population. So you are actually minimizing the population, even though.
But if you have gradient descent of the population, you have correlations. So how can you analyze
correlations with the samples, or in which kind of correlations?
Between the state of the network and the sample. And so
here we are doing one pass, so we don't have, so the process is Markovian, but the ODs that you would get by doing gradient descent to the population are exactly equivalent to the one that you are doing one pass in this regime. So that's what we proved. So we are not doing this gradient descent to the population, but implicitly we are doing that.
okay. Thank you very much.